Okay, let's discuss the Landau approach, Landau mean field theory if you like. Here we escape the usual difficulty, main difficulty of statistical mechanics, bypasses main difficulty of statistical mechanics. What is the main difficulty? Partition function from a given Hamiltonian. We are not going to do that. Instead, we are concentrating on a phenomenological approach. Or theory. This approach is not interested in finding or determining whether there's a critical point or not. It is assumed at the beginning there is a critical point, and there are two ingredients, main ingredients. One is the order parameter. You know, this is a small thing near the critical point. And Helmholtz free energy and around the critical point you can expand the free energy in terms of order parameter. So it expands F as F0 plus F1 phi, F2 phi squared, F3 phi cubed, F4 phi to the 4, etc. If you cut the series at phi 4, it is a phi 4 theory, known as phi 4 theory. So, well, this can be ignored. Okay, you can always change the energy scale. Origin of energy is arbitrary. You can choose it so that the first term is 0. And if you are trying to understand ferromagnetism, for example, order parameter is magnetization, which is a vector. Okay? If order parameter is a vector, then can you have odd powers of the order parameter in this case? Odd powers will be vectors. F is not a vector, so you can omit the odd terms. You only have m dot m to get a scalar from a vector, which is m squared, which is phi squared. So you write F as F2 phi squared plus F4 phi to the 4. Well, F2 and F4 are phenomenological coefficients. These are maybe functions or assumed to be functions of temperature. Okay? So we can go to critical temperature by using these coefficients. And equilibrium corresponds to the minimum of the Helmholtz free energy, which can be found by putting the first derivative to 0. Well, here we are talking about Landau free energy. So the conventional Helmholtz free energy requires an equilibrium. Here we are assuming that there is a quasi-equilibrium state where we can expand the free energy in terms of the order parameter. So let me remind you that quasi-equilibrium that's why we can call this Landau free energy. Okay, now let's see if we can have magnetization. It's very easy. Well, why are we able to omit the higher order terms? Because we are expanding near critical temperature. And near critical temperature, these order parameters are small, aren't they? Well, small term, higher powers are even smaller, so you can omit them. Now let's see what that condition gives, considering a 5-4 theory, taking the expansion to power 4. So we have these terms. Okay? And if we take the derivative, and put it equal to 0, it is 2f2 phi plus 4 f4 phi cube. So one of the solution is phi equals 0. The other solution is phi equals plus or minus square root minus f2 divided by 2f4. Corresponding to equilibrium. Well, we must have F4 positive. Let's see that. Because we want the free energy to increase away from the minimum that is needed for stability. Then we have two cases. If F2 is negative, we have three stationary points, aren't they? If F2 is negative, we have a positive solution for phi, 2 roots and a 0. If f2 is positive, we have only phi equals 0. So we have the following situation then. Lambda free energy, something like this. F2 positive. There is only one stationary point corresponding to phi equals 0. And if F2 is negative, we have the following situation. So we have 3 roots. Huh? This is F2 negative. Very clearly seen from our very simple form of the free energy. Where is the critical point then? Critical point is where F2 changes sign, isn't it? So, critical point is where F2 changes sign. From positive to negative, for example. So you have a finite magnetization. Now let's expand F2 and F4 in powers of T minus Tc. You can write F2 as A T minus Tc. See, it changes sign when temperature is above Tc, it is positive. When T is smaller than Tc, it is negative. So as temperature goes to the critical temperature, F2 changes sign. F4 can be taken as a constant, B, so that phi is 0 for T greater than Tc. Phi is plus or minus A Tc minus T over 2B for T smaller than Tc. So we have different than 0 result for temperature smaller than the critical temperature. Is that okay? Very simple idea. Well, if you write the free energy, plot the free energy as a function of phi, you have the following picture. Lambda free energy as a function of order parameter up to phi 4. Here is the result for T greater than Tc, isn't it? Minimum is at phi equals 0, one solution. At the critical temperature, this free energy have excursions from phi equals 0, and that doesn't cause any energy, those excursions going from away from 0 doesn't cause any energy. That means there are fluctuations at the critical point. And here comes the result for T smaller than Tc. Now you have three solutions, three roots. That corresponds, if you think about this as magnetization, ferromagnetism, then it corresponds to a finite magnetization below the critical temperature. Well, you can have a simple model for good for ferromagnetism. Let's take a mean field theory and explicitly calculate the free energy as a function of magnetization to see the same thing. Okay? We are not talking about or trying to find the existence of a phase transition. We assume that there is one. There is a critical point, critical temperature, and we just expand the free energy in this approach in terms of the order parameter. Now let's go to the ferromagnetism. Again, write everything within a mean field approach. Ferromagnet so if we know what energy is and entropy is, we can write explicitly free energy in terms of the order parameter, which is magnetization in this case, which goes to 0 if you cross the critical temperature. Well, E can be written as BdN, if you like, and you can write B magnetic field as applied and the local field in Curie-Weiss or Weiss model is NKB Tc m over m0. This is Weiss model. That means mean field approach. We have explicitly the energy, which is minus NKB Tc over 2 times m squared. M here is m over m0. This is induced magnetization, if you like. Now let's find the entropy. What can you write about entropy? Can you tell me? There are two expressions for entropy, Kb ln omega, or in terms of probabilities. You can write it in terms of probability of finding an upspin up state or down state. There are two states. So let's take that. Entropy is minus NKV. PR and NPR. Since we are dealing with a spin 1/2, let's do that problem. Simplest. In this case, you can write entropy as minus NKB. We have two states. Probability of up state, and then P up, and P down, and then P down. Oh, very pedagogical example, I think. Now you can follow everything. All we can do is to write P up, which can be written as 1 plus M over 2. P down as 1 minus M over 2. When you add them together, you find 1, normalized probabilities. So entropy becomes, in this case, explicitly minus NKV, 1 plus M over 2, ln 1 plus M over 2. Well, it is like a toy problem, isn't it? 1 minus M over 2, ln 1 minus M over 2. So we can solve this explicitly. You can rewrite this as NKV, expand everything to ln 2 minus 1 plus M, ln 1 plus M, minus 1 plus M, ln 1 plus M. Am I doing it correctly? 1 minus. Okay. So that F, which is E minus Ts, becomes minus NKV over 2 Tc m squared plus T 2 ln 2 minus 1 plus M ln 1 plus M minus 1 minus M ln 1 minus M. Okay, that's it. Very simple, okay? So, if we plot this, we find exactly the same thing as we did before. We find as a function of M, lambda free energy above the critical temperature. M turns out to be 0. at T equals Tc, that's the form of free energy, and below it is something like this. So that we have magnetization below the critical temperature. And this is for T over Tc 0.8. You can do that yourself too. So at T equals Tc, symmetry changes, isn't it? In the vicinity of the critical point, and that was the approach introduced by Landau. This is important. Vicinity of Tc at that, around that means around T equals Tc, to go to the other side to get a transition, we can expand this logarithmic terms 1 plus x as x minus x squared over 2 plus x cubed over 3, etc. Okay? M is very small around Tc. X is very small, so x squared is very much smaller than 1. You can write this expression by expanding the logarithmic terms as nkb over 2 t minus tc times m squared plus tc over 6 times m to the 4. You see, we are back to phi to the 4 theory. M squared and M4 appears. And essential information is here. The coefficient of M squared terms changes sign as t goes below Tc or above Tc, isn't it? Above Tc, it is positive. Below Tc, it becomes negative. Huh? That coefficient, T minus Tc. The critical point corresponds to the point where the coefficient of m squared changes sign. This explicitly gives us a way to discuss the phase transition, second order phase transition, isn't it? Is that simpler? What are you going to do to find these points? Exact points where the free energy has minima or stable points. Take the derivative, put it equal to 0, isn't it? That's that simple. So this is, again, a very simple introduction to Landau approach, Landau mean field theory. Do you have any questions?